This is hopefully we're all at the right talk now. Hopefully harder to get lost now we're all online. But this session is Frictionless Allocators. I'm Alisdair Meredith, Senior Developer at Bloomberg, and long-time participant in the C++ standards process for any who don't know me. And the goal of this talk is to describe issues that we have with the existing allocator model that we inherited from C++11, and talk about some of the ideas I've got for improving the feature in the language as we go forward that can take a lot of the friction, hence frictionless, allocators out of the system. So, quick outline of the talk. Why do we want allocators? Why are they useful? What do they look like? And you can read the bullets. I'll get moving because otherwise I'll be running late. Traditionally, I always run long on these things. So, start with the basics. What is an allocator? What do I mean by an allocator? And I have a simple definition. It's a service that grants exclusive use of a region of memory to clients that will need memory. And nice clients will even return that region to the service when no longer needed. Otherwise, you're in some kind of garbage collected environment, which might work, but that's not necessarily what we need within this model of allocators. Why do we want allocators? Question, is the new operator itself not good enough? And the basic answer that I have told you repeatedly is performance, performance, performance. The main reason that a lot of people really want to take control of allocation is that you can significantly improve the performance of your programs in specific circumstances when you have extra information to supply the system. But other reasons, which were more the reasons I got into the allocator business in the first place, are things like instrumentation to have a better understanding of how your allocators are working and what the usage within your program is, and trying to allocate into special memory regions. Quick talk on performance. I don't want to go into too much detail on the performance motivation here. We've had a couple of talks on this in the past. In particular, I want to refer to a John Lako's talk on the value proposition of allocator software. He's provided some papers to the ISO working group on allocator performance based upon some benchmarks on typical allocator use to demonstrate that when using allocators in the style that Bloomberg have been using allocators, we can typically achieve under these benchmark circumstances a factor of 3 to 5 speed up on what seems to be relatively common usage patterns. And if you, keyboard's out of control of me again, and potentially an order of magnitude in some of the more extreme cases of our benchmarking. So, how do you get a faster allocator? A general purpose allocator in your system that basically operates anew. It's going to try and minimize contention for multiple threads trying to cause allocation at the same time. That used to be a major bottleneck. And if we know we're in a single threaded application, or our usage within our current application will only ever access the allocator for a single thread, we can provide a more optimal allocator for those circumstances to remove all kinds of thread contention and synchronization that can improve throughput on the allocation there. Simplified bookkeeping, if we never reclaim memory, this is another common pattern where, say, I have a chunk of memory that I'm just going to allocate on the stack, and then just let that go out of scope at the end. And if in this kind of model, we can say, I'm just going to keep moving my pointer through that memory, and you can give me the memory back, but I've just got this limited pool. Once it's gone, it's gone. That gives you a real simplified bookkeeping, which again can give you a faster allocator. But this is not where the real performance of allocators come from. The typical case of what reason you get performance out of allocators, the reason you want them, is memory locality on modern systems is the much more important factor for performance over the long run of your application. So the more we can keep allocations local for our particular data structures and have different allocation regions for different data structures, the better the chance of with that locality of keeping the memory that you're hitting with level 1 or level 2 cache, and that will greatly have a speed of performance on your program. In this manner, you can have different memory pools for different data structures. That will minimize what John Lako's calls diffusion on a single task, where over time, even though the amount of data you're using in your application might not change. It just diffuses through memory, so it's now spreading across lots of different data pages, which means as you jump through your data structure, you're paging in memory from all over the system. If you can keep your memory pools localized, you're going to have a much smaller working set, and that is, I say, a large part of where performance can come from. Another benefit is when you've got long-running applications, as you're claiming and releasing memory all over the place, you get the effect of fragmentation, where even though you might still have a lot of free memory on your system, the largest individual chunks that are available start to shrink as just memory gets allocated and removed at different times throughout the process. Some of the techniques we can do with allocators, such as we say allocating regions off the stack, which naturally reduce the idea of fragmentation of long-running processes. So again, that's another part where performance and reliability can come from. And yet again, no synchronization if we know that the processes, that all the allocations within the current will be local to the current thread and not shared between threads. So again, we have two common strategies. We have to try to improve locality. A common one is we can allocate off the thread stack. So typically we're having, say, a 2K array or something, and that we might buffer for local use in that function. That's as local as we can get, and that's really going to keep data in the level 1 cache ideally. And the other notion is that we're going to manage different pools, so that if I've got a data structure over here, that will have a pool managing it, and I can try and pre-allocate that pool so it's just one contiguous region of memory, and then I can farm that memory out between different allocations within that task. But if I've got a different data structure, that will have its own pool with a different, hopefully contiguous region of memory, and that again helps reduce diffusion, reduce fragmentation, and improve the locality on the system. Now, the idea of using pools like this is, of course, largely how, which is pools for objects of different sizes, it's largely how operator new is implemented. So to an extent, they're reinventing the wheel you already have. But the goal is if we can have distinct pools for different data structures, that's where we get the locality that operator new, not knowing about our data structures, cannot give us. In addition to the basic performance benefits we've been talking about, though, the other thing we can get from custom allocators is additional functionality to support debugging or logging, basic telemetry services, profiling, and interactive querying of our telemetry, which is really handy when you're writing your test drivers to ensure that you're not leaking and you're not double deleting, and the performance of the memory is you're allocating from the correct pools all the time the way that you expect. So having some kind of debug memory allocator or the telemetry memory allocator for testing is really helpful. Now, the other aspect that we can do with C++ 11 allocators is we can potentially try to address special kinds of memory. So this typically has been something like shared memory, and Boost into Process Library is a good example of where you might want to have shared memory allocators so that you've got a common data structure, a vector of strings or a vector of graph nodes or whatever, that is loaded ultimately into different memory regions in different processes, although it's the same data structure. And the way you handle this is with some kind of offset pointer that says wherever the start of my data structure is, I've got this fancy pointer, kind of like a smart pointer, but not connoting ownership, just it's a different way of navigating the data structure that says, as long as I know where the root of the data structure is, I can navigate to any other node within there, even if it's going to a different address in different processes. And another common use case is something like trying to address video memory on video cards, and you have some very heterogeneous processes that are running around these days. And again, this is the kind of thing that the C++ 11 memory model can handle with some kind of notion of supporting fancy pointer types, which are user-defined types to map that pointer to the actual memory in your process. So just to spell out where we're coming from, we've made some claims that allocators are good for performance. We've been talking about this for years. We have done our own benchmarks to demonstrate that, but there's a question that if we are benchmarking our own software to give the demonstration of what we've done, is that a reliable set of benchmarks? So we reached out to Emery Berger, who's a professor at University of Massachusetts in Amherst, and is the original developer of the Horde general purpose memory allocator. So this is the idea of trying to write a better new. Emery was one of the early folks trying to do that, and he's long had an interest in the performance of memory allocation. We've asked him to basically help audit our, come up with his own set of benchmarks to see if what we're talking about works or not. So we thought, hopefully can help bring some more authenticity to the methods that we're working with. And we came up with a couple of basic ideas we're trying to go here to demonstrate the value of custom allocation. And Emery's gone further. He's trying to find automated tooling to find opportunities that will highlight on our known allocation patterns opportunities to improve your existing code with the use of custom allocation. That's further down the line. We're not at that part yet. But again, his main thing is to see from our existing work, are the optimizations we think we're seeing really there? So we've taken some existing, essentially Bloomberg code. It's built around the open source BDE library where we have our own custom allocations and some code that they're using it. So the buffer sequential allocator is our basic high performance allocator for allocating essentially off the stack or above. You put your stack on, small array on your stack on the call stack, allocate out of that, and hopefully you never have to go out to the heap. If you overflow that stack, it will go out to the heap and get another buffer so that we don't run out of memory, but hopefully it's relatively small. We hit the stack, the heap relatively infrequently. We just got these large contiguous buffers that support our allocation. And again, when we go out to scope, hopefully we never have to hit the heap and everything just comes off the stack. So taking our existing code that does this, we have two examples, a stress test, which is an artificial example written to stress with the composition of sorts and filters on the data to just really, trying to create a heavy workload to see how our allocations work in that pattern. And Moda was an abstraction of an actual workflow that comes through our main application. So something like an Excel worksheet with a bunch of formula and a lot of data running through that to see how that would, as a more realistic real-world example, does the performance profile show there as well? And the essential idea is we're going to, while our existing code is written using and aware of this allocator, we've done the work to put the allocator in. What happens if we shim out that allocator and say, we don't touch the code, the actual attempts to go to our local allocator instead just go straight back onto the heap. So you effectively sidestep the allocator and the benefit it's trying to bring us. So this is what Emery showed. I think this was compiled on Macintosh. 03 replacing this buffer manager with his shim to go to new. And we compared with both the system new and with the Horde allocator. And you can see, if you look across, the idea of trying to replace the system new with a better allocator, which is basically switching to Horde, because the red bars, there's a benefit, but the benefit we get from using our custom allocation strategy was clearly more significant. And you could indeed combine the two because there's those cases where it still does have to go out to the heap, and then hopefully you get the best of both worlds. But we believe, you can see this, the significant benefit comes from switching to this buffer sequential allocator in the first place. But the overall performance is 25% improved, 25% faster with custom allocation, and that's like a 50% throughput improvement if you invert. I don't like these things that trend towards zero because you get, if you double your speed and then have tenfold the speed, the tenfold doesn't look anywhere near as impressive again as the double. So, but this is a slide I got from memory. So that's our motivation as to why we want to be doing something with allocators. Now we'll take a quick look at how allocators work in C++20. Again, this is largely a revision material, which is trying to go quickly. In C++11, we have the notion of allocator traits, which is this big class template which provides all the allocator services that your program is supposed to use. So we get a bunch of type tests that will help describe how your allocators work. And most of them have anything that says see below, I don't provide below. That just says there's a formula here, a meta program, that can be used if your allocator does not supply a type of these names. So allocator traits will adapt to a minimal allocator implementation to provide the whole service, trying to simplify the idea of writing allocators. So this is just a general walk through the basic interface. Key part is you're going to want to, at some point, allocate and deallocate memory. So as you can see, we've got a bunch of static functions in allocator traits, and each of those functions you pass your allocator to. And this is the intended usage pattern of allocators in C++11. You don't use the allocator directly. You pass it to one of these methods in allocator traits to say, please do the work of providing the allocation. And again, if you don't provide all these methods, you have to provide allocate and deallocate. But any of these other methods, if you don't supply it in your allocator, the allocator traits will synthesize it on your behalf in terms of all the other operations. And the interesting things to notice is that the allocate and deallocate functions work with the pointer type depth, which means they work with whatever kind of fancy pointer for your shared memory or your video RAM, whatever extra services your allocator provides. If it wants to work with fancy pointers, that's how allocate and deallocate work. But the other part of the interface is construct and destroy, which is a customization point to say when I'm constructing an element using my allocate, using this memory region of the allocator, if the allocator needs to interact with that in some way, it can, by overloading construct and destroy to being how you create your dynamically allocated elements, the allocator can insert any extra information it needs to at that point. Those APIs, you'll notice, although the allocator is an allocator of T, an allocator of a specific type, a construct and destroy will work with any type and traffic in raw pointers. So you have to now be able to switch between the raw pointer and the allocator. So that's just a subtlety of the allocation. And I had a point that I've forgotten, and I've got too many slides to go, so I'm just going to have to run straight through it. But the interesting point was to be aware that the allocator facility, the allocate and deallocate facility works with fancy pointers, construct and destroy, do not. Sorry, that will come back up a little bit later when we want to see what we can support going forward. Then we have this whole problem with propagation traits, which you may or may not be aware of. Given this is a C++ now audience, I'm expecting most of you are familiar with some of the alternatives of the C++ standard. And again, this is a feature since 2011. They all have a default, which is by default, none of these traits default to propagating. They all say don't propagate. And we have this funky select on container copy construction because the trait for copying, for how to propagate allocators on copy constructors is actually a function and not a trait, just for extra fun. So that was 2011. How did we improve things in 2017? So this has been hopefully shipping for a little while now. We have the is always equal propagation trait that says these two, any memory allocated by any of these allocators will always be usable in any other allocator of the same kind. And that allowed us to improve the acceptance specifications on a bunch of containers, because this is a common property of stateless allocators like standard allocator itself. And we also provided the PMR polymorphic memory resources facility in namespace std PMR. And this is a way of supplying your allocator at runtime of different kinds, and it's polymorphic. I say allocator, the standard says memory resources. I've been in Bloomberg too long, and what the standard refers to memory resource is exactly what we have referred to as an allocator. So hopefully I will not get too confused in my terminology. I'll try and say memory resource, but if I slip, hopefully you'll know what I mean. We have the PMR containers, which is a set of type aliases or alias templates that allow you to plug the PMR allocators or memory resources directly into the existing standard containers. So we didn't need to write new containers. The existing containers all do the work correctly, because that's what the allocator traits brought us. All we're doing is plugging in a different allocator rather than STD allocator, and then everything just works with this new polymorphic memory resource model. And the other change in 17, which may or may not be noticed, is if you have fancy pointers, so you're doing one of these other shared memory allocators or something similar, the allocations that return from those shared pointers must be contiguous iterators. So you can't have funky pointers that say, I return, here's a list you can walk over memory. No, it's got to be a single contiguous allocation now, which I don't think anybody supported anything different anyway, other than me writing a few crazy test drivers. So it clarified what people already thought the rule was. So as you see, in C++17, we have this new is always equal trait added to the set. And in C++20, just for extra fun, allocators become const expert. This is supporting the standard for basic string and for vector. And user types that follow the appropriate rules for const expert allocation. I'm not going to go deeply into that in this talk, but it's good to know that this extra facility is coming. The key thing when you have const expert allocation is you can use const expert allocation within a const expert function, but the objects allocated within that function all have to be destroyed by the end of the function. So you can use them to compute a result to have your pick, but you can't return const expert allocations out of a const expert function. So they've got a limited use, but that use can work. It's targeted for, essentially this was intended for support for where some of the reflection facilities might go, where there was clearly going to be a need to have some kind of allocation to navigate your reflective meta programs at compile time, but the whole effect would happen within that code. You wouldn't need to propagate the vector and string out of those functions. And again, there's ongoing work in C++23 to see how much more we can weaken these constraints and maybe have some more facility here going in the future. So back to the basics. How does standard PMR work and what does it provide you? The basic notion is that any memory resource, which is something that can provide, it's a resource that can provide memory to your allocator, derives from standard PMR memory resource, which is a pure abstract interface class that says this is how you provide memory. Your own resource will therefore override the pure abstract members and they'll actually supply the memory as required. Clients who want to use the memory resource essentially store a pointer to that resource, which we say is like a vtable. The idea is that when you construct your object at construction time, you're going to bind the resource that will be the way to retrieve memory, to produce memory for that object for the lifetime of that object. And like a vtable means, in this notion, that when you copy, swap, anything where you might want to propagate, where you're assigning the memory resource pointer doesn't propagate just the same as a vtable wouldn't propagate. You're saying, okay, I've got my pointer, this is how my object's going to have memory allocated for its lifetime. That is quite independent of the value and the other behavior of the type. And this provides us a couple of benefits. The key thing is that once I have my memory, I'm talking ahead of myself. When I'm trying to make sure that I do not leak references to my memory resource within my object, there's a danger of if my, 2 seconds, get myself straightened down, talking myself into corners, sorry. Mind's racing and you're trying to give the answer before you stated the problem correctly. So the answer I'm trying to get to is I allocate my resource, and then after that I will create the object that uses that resource. And because I know that the resource cannot be accidentally assigned to another object, the lifetime is now constrained so that I'm not going to leak a reference to my memory resource by further on trying to propagate that object and its allocations to another object of the same kind with a different allocator. When I try and do that assignment, it's going to say, okay, if the allocators aren't the same, then I'm going to have to do something different other than just transfer with a move-like semantic. I'm going to move on. I've got slides that talk about this again better a bit further on, so I'm getting ahead of myself, I think, for the next time. So this is what standard PMR memory resource looks like. There's a virtual destructor and some protected virtual methods. We're using the non-public virtual method pattern so that we dispatch to it these virtual functions from some public non-virtual functions. And this allows us to have a default parameter for the alignment, which just means that we've got the sense that the virtual functions always have two parameters. There's no funky messing around with, do I have alignment or not? And what happens if I override a function and change the default of the alignment? We don't get into that. Just having these straight public functions makes life much, to do this back, makes life simpler. And this is the interface the user interacts with, which has the non-public virtual function interface. The virtual interface is not public, the public interface is non-virtual. And finally, the other thing to notice, because the idea of polymorphic memory resources, I want to be able to provide memory for all sorts of different types. This is not a template like most C++ allocators in the C++11 world. We represent memory with a void star. So you always have to cast it into the type you want to use. When your allocator provides memory, you can do whatever kind of allocation scheme it wants because it's going to come out again as a void star. So that's our vocabulary type for describing memory that has been allocated and will pass through the allocators. Finally, we have the is-equal function, which says, do these two memory resources, are they interoperable? Can they exchange memory, but it's been allocated by one through the other? Typically, that's just the identity question to say, are they literally the same object, which is the most common metric for, can two memory resources interoperate? I'm not aware of many strong use cases for overriding do is equal, but one example might be if I'm writing an allocator adapter that adapts a more traditional C++ allocator and then tries to host it with a memory resource like interface or an adapter, I might want to delegate the answer to that question back to the underlying objects themselves. So I might do is equal say, oh, I'll be both with the dynamic cast. Wrappers are the same kind of thing, and if we are, can they interoperate? So it gives you a customization point for that. I don't think it will be used very often. When we get to the standard, we also provide use standard memory resources. The new delete resource delegates get the allocate function to the new and delete, new and operator delete. The non-memory resource is even simpler. It never allocates memory, it just always throws bad alloc, which is a very, might not be a terribly useful resource, but often we end up building chains of resources. So one resource adapts another resource, adapts another resource. And it can sometimes be handy to have the non-memory resource at the end chain to say, yeah, I'm not going to keep trying to find any more memory. You've come to the end of the line. The third resource, which is, again, kind of usually the resource adapters and kind of is get default resource, which says, if I have an API that's trafficking NPM on memory resources and I don't give you that resource, then which resource should I use? You didn't tell me. I default to the system default resource. And that's customizable. So, for example, I'm writing a test driver, I might install a default resource that does all my instrumentation and testing and tells me that everything has gone through to the default resource rather than using its other, hopefully more appropriate resources in that case. We also provide some classic implementation. So the monotonic buffer resource is the one I spoke about, where you're going to try and allocate out of, I've got an array, and the monotonic buffer just simply uses up that array until it runs out at the end, and then typically that will then fall back onto either the default resource, or you might, as I say, back it up with the non-memory resource to say, when I run off this stack, don't go to the heap, just say we've done it, it's all exhausted. Then we've got the synchronized and unsynchronized pool resources, which are the classic memory pools based upon allocating objects of different sizes into different code pages. The difference between synchronized and unsynchronized is if you know that your allocation use is never going to be access to multiple threads, you'll get a performance boost from using the unsynchronized pool resource. If you do need to be concerned about different threads all pulling from the same resource object at the same time, then you would use a synchronized pool resource. So, idiom in usage. Keeping here something I was just spoken about before I get here, but I know it's coming up in a couple of slides. So, as I tried to speak earlier, memory resources are objects that you will then pass a reference to them, typically by address, to the containers and other things that want to use that memory resource. So they're typically going to be scoped within a function with a lifetime, which, as I say, guarantees the whole lifetime benefits that anything that's using that allocator should occur after the actual concrete object itself, and that prevents leakage of pointers through to those resources. If you have long-running resources, you want to obviously use some kind of long-running resource itself. So something like the system new delete operator says, if I'm going to have new delete resource, I'm going to want to allocate things that are going to outlive this function call. So I've got a factory function trying to return something out of the function. In those cases, you want a more global friendly resource, which is something like the new delete resource. That's why they exist. We have the notion when we talk of default, object, and global allocators. The default essentially is a system-wide global allocator, a system-wide allocator that will be used by default. Global allocators are for static objects or objects that are going to exist beyond the function. Well, you should install those. But the object allocator is the allocator we're installing in a specific object. I'm creating a vector, a string, whatever. The allocator I install in that is what we refer to as the object allocator. And the question then comes up that I'm now writing a member function, like insert or something similar, that wants to allocate memory. Which allocator do I use? I use the default, the object allocator, or a global allocator. And the general rule is, if I'm allocating something that's going to persist beyond this function call as part of the data structure of that object, so it's going to be an element constructed within the vector or a list node or something similar, in those cases I use the object allocator. But if it's just a temporary transient object that's going to be created to help compute a result, but is not going to be stored within the lifetime of the object, in those cases, even though it's a member function of an allocator-aware object, you go back to the default allocator because what the object you're constructing, say a string to do some extra, do some logging that's then not going to be stored long term, is not a part of the whole object system itself. And if you're using something, if the user installs something like a monotonic allocator, those allocators that just consume memory until they exhaust it, you don't want all your temporary objects that are transient within these functions consuming that long-term storage that is a much more limited resource. So the default is, if it's not a part of the data structure, even if it's called from within a member function in your object, you want to use the default allocator, not the object allocator. And so if you know it's going to be a very long-term storage, like a static data member, a static object within your function, in those cases you would directly go to a global allocator like the new delete allocator, or a similar custom global allocator you've written yourself. The key thing to note about PMR is it has no support for the fancy pointer idioms. This is because the allocate function, in order to be type generic, always returns a void star. You can't provide an override for a custom allocator that returns something that's not a traditional pointer, because that's then not going to match the override signature. So you can construct a similar facility for your specific fancy pointers, but you would be duplicating the work of PMR focused on your type. This is not something that falls out of the existing facility. So that's our limitation. Let's start a very quick example. We've got a simple factory function. We're going to try and make a string. So as I said, the idiom is, first of all, we create the resource, the monotonic resource. This is a really poor monotonic resource. I've not actually given it a buffer to hold, so a bad example. But yeah, assume I've got an array that this monotonic resource is now going to hold the string in. I create the string after the resource so that I need to refer to the resource, but it also means that when I exit the function, the string cleans up and there's nothing left that's got a reference back to the resource res. Only this is C++ 11. We have potential return value optimization here. And in this case, I would now actually, if the return value optimization applies, I now risk leaking my pointer to this stack-based monotonic resource. This is a bad thing, and the compiler can't help us out here. We just have to be aware of this concern. And the trouble is we can't guarantee the RVO in C++11, so you have to be aware that it might or might not be can't. At least in C++17, they have a guarantee that this is bad behavior, because now the return value optimization is guaranteed by the compiler. So again, this is a problem. How do we resolve it? We just have to force a local copy that will then use the default allocator, so that what we propagate out is then, a copy of the string we made. So it's not the nicest thing in the world, but at least the fix is relatively simple. And hopefully, as compilers become more aware of these idioms, we can hopefully start getting some warnings in some of these cases. But knowing that what you're caching is an allocator that will have an impact is very domain-specific knowledge that might be more appropriate for static analysis tools. But underlying all this, I've not spoken to, and this is probably why I was stumbling over myself, because this is the other key part of the PMR model, is what we call the scoped allocator model. And the idea is very simple. Every element in the whole data structure is using the same allocator and memory resource. So that's how we're going to guarantee our locality when we're having everything put in our pools and so forth. We don't want to have different allocators scattered around, and it's also how we guarantee that when the building on the lifetime memory resource and object beneath, if I've got different allocators throughout the data structure, it becomes much harder to reason about what's the lifetime of the memory that has been allocated by these different allocators in different parts of the data structure. So it's a very simple model. Everything in that whole data structure uses the same allocator, and that also makes it relatively safe when I'm trying to use move semantics. As long as everything uses the same allocator, I can just transfer the pointers around, and I know the whole object class graph is going to be good. So class design, every member of the object graph, i.e. all bases and member classes, when you construct them in the constructor member initialized list, all have to use the same allocator. Now there's an invariant, any dynamically allocated persistence data uses the same allocator. This is guaranteed when you use the Allocator Traits model with our PMR, because the allocator supply hooks in to say, whenever you try to construct something, I will also add the allocator arguments in to retain this important invariant. I say the key benefit of having the whole persistent data structure with one allocator is that's where we get the performance benefit when we're trying to avoid that notion of diffusion, memory spreading throughout the system. We give it an allocator to keep it local, it stays local. And I say also makes it much more easy to reason about the lifetime guarantees of the memory within that data structure. And so the key implication is that within the PMR model, allocators can never propagate, which is often a stumbling block for folks who like to think that if I copy an object, everything copies and I don't have too much more to think about it. It's intuitive notion coming from a lot of value-based C++, so that until you deal with something like the scoped allocator model, it can be kind of counterintuitive that some of the data members, once you've created them, never change. But that's the model we have. But yeah, because the problem then would be, as I say, any swap or assignment could invalidate everything we've done there. Standard PMR allocator. So this is, especially when I start getting confused between the term allocator and memory resource. This is a C++11 compliant allocator that works with the allocator traits to support being a general purpose allocator that wraps a generic memory resource. So C++17, we put this thing into standard PMR. Essentially, everything you're seeing on the screen is part of 17. For C++20, we default the template parameter to be standard byte, and we delete the copy assignment operator because it will just catch bugs. You're not supposed to overwrite these things. You're not supposed to assign to them. They're set up construction and then they're done. In theory, nothing should end up having to hit that. So if you do accidentally call these things, having it deleted will just flag up those errors more easily. So In order to support being a general purpose C++ allocator, we have to have the value type that says, I might be a polymorphic allocator that can handle allocating for any different kind of object, but now I'm a standard PMR allocator. I'm an allocator for a specific value type. And we also have the polymorphic constructor that says I can copy and handle. I can copy allocators for objects of a different type that happen to use the same pointer as me. Nothing changes on the basic allocation interface, but the addition for C++20 is we also have this allocate bytes and allocate object methods. The notion here is by defaulting the standard the template parameter to standard byte, standard PMR allocator of byte is intended to essentially become a new vocabulary type allocation, so that rather than through allocator traits, I might go through this specific interface when I'm using PMR allocators in non-generic code, just to get an easier tracking onto this facility. Again, that's not something that is talking. I don't want to go too deep into it, but with C++20, we're trying to start promote the notion of standard PMR allocator. Angle diamond style is a specific type that we can use because it's not tied to allocating a specific type. That's our preferred vocabulary. Limitations of PMR. So it solves the vocabulary problem that if I've got containers using different allocators, they suddenly become different types. That's a vocabulary problem. And yeah, so we solve the vocabulary problem by consistently using PMR types, i.e. it is the vocabulary problem. We don't support fancy pointers, as I said, no special memory regions, no shared memory. There's an extra allocator pointer now stored in the PMR object itself, the PMR allocator, and then every object that's working within that system that uses a PMR allocator, duplicately storing that pointer, we're just padding our data structures a little bit. And again, all allocation is now a dynamic dispatch, and John Makers talked about why, in practice, that dynamic overhead for the actual dispatch on the allocation should be essentially negligible. I'll defer to John's stuff. I don't want to go into that in too much detail now. So the Bloomberg Experience using allocators, which is, of course, where I come into all this. Bloomberg uses its BSL MA allocator model, which is the progenitor for what became PMR allocators. We find when you have a use case for allocators and performance critical code where you have the context to say, I know I can use an allocator here intelligently, that'd be the big win. From my perspective, I spend all my time writing test drivers and having the ability to instrument our code to make sure that the allocation behavior is what we expect it's working correctly has been a huge win. And the end users downstream of us, although they like the performance wins, we still hear, especially from new users, bridling at the code complexity that comes from having to write all the extra code to support allocators in different ways. So it's a big win. It comes at a cost. So what are our sources of friction with PMR allocators going forward? Well, the big issue for me is there's a bunch of unsupported use cases that we can't, sorry, just we can't take it around to. I'm running slow, but I still have half an hour to go. No, my slide telling me I've got 40 minutes. So I'm about right there. Unsupported use cases. There's a bunch of places where even if I'm correctly doing everything I can to use PMR allocators with the scoped allocator model, there's a bunch of places a scoped allocator model can't reach. A classic example is a simple C-style array. There's no way I can tell all the, so I've got an array of strings. I can't give the allocator to each of those strings consistently in a single way to say that array is all built using the same allocator. I can provide initializers for each individual string in that array if I want. And there's no consistency, and unfortunately, they all do get the same one. And similar issue with aggregates, because an aggregate like standard array is not allowed to have constructors. I can't provide the constructors to supply the array, so I've got to manually again, push it all the way through the aggregate initializers. It's not on me to do that correctly. And then as soon as you get to the copy constructor, they're going to do the wrong thing anyway. So that's a problem. Lambda object, if I capture something that's in a PMR allocator aware type, I can be careful with my capture with all the different syntaxes we've got now to at least inject the allocator I expect by using the initialized capture syntax. But if that lambda object is ever copied, it's not going to follow the scoped allocator model rules. So again, lambdas don't work great. Structured binding, similar problems. Default member initializers. If I do try to provide a default member initializer, it's going to end up either using it's going to essentially using the default allocator or the I might provide a global allocator there, but whichever allocator it's using, it's not the one that's being supplied to the constructor. And that's therefore going to violate the rule that the whole data structure uses the same allocator. So default member initializers can be a problem here. And again, ultimately, the problem's recursive because I want to apply the scoped allocator model. This was the example that got me fuming and started down this whole line. A vector, a standard array of string. I correctly provide the right allocator to the vector, but it can't provide that allocator to the strings because they're all held in a standard array, and standard array cannot support the scoped allocator model to propagate the allocator down to all the individual strings for each different element in the vector. So these are problems that we need to find some way to solve. And keep speaking about allocator propagation. Hopefully I've said enough, so I don't want to go too much about that now. But again, this is a source of complexity and confusion with C++ 11 allocator models, that we now have these fine-grained traits that control the notion of propagation. And that leads to complexity in the general case, because we've now got multiple fine-grained traits that are controlling different aspects of allocator propagation. So what does it mean if they disagree with each other? I'm trying to write a support an allocator that maybe says, don't propagate the allocator on swap, but do propagate it on move assignment. So how does swap work if it can't use move assignment, or vice versa? So getting consistency in these cases is frustrating, and it's something I don't want to be worrying about too much. And the trait for copy construction, as we say, is actually a function call. And even worse, the default one doesn't do our scoped allocator model. So if we're trying to do scoped allocator model, that's one customization point we have to use. So the syntactic overhead of going through allocator traits, again, it's high. This is one of our sources of friction. So mandatory, every time I want to construct one of the objects in the memory of allocators, I don't do an in-place new or anything else. I have to go through allocator traits to construct, which is very strange expert level code. It's not something your average jobbing programmer is going to want to deal with. In practice, we end up doubling or worse the number of constructors to allow for the optional allocator, because we want to be able to construct things without thinking about allocators, but plug it in when we do know. So the end result is in C++ 98, we just provide the default allocator argument as the final argument, and that hopefully avoided having to double by providing them separately. But it turns out that doesn't work when you have multiple defaults. So for C++ 11, unordered map had 8 constructors, which is a fairly because a lot of power support allocators. C++ 17, we fixed it for all the cases we were missing, and it now jumped up to 15 constructors, many delegating back to the original 8. But when we did them, we thought we correctly implemented an allocator aware type as it was. So even the standard can get caught out with the folks who know what they're doing here. And that also led to, once we had varied templates in C++ 11, it's not very easy to pull out the last argument and say, is that my allocator? So we switched to a different style of signifying the allocator to say, yeah, if you've got an allocator aware constructor, we'll have an allocator arg to indicate the next argument is going to be an allocator, and then we'll have the regular set of constructors. So that became the preferred idiom for passing allocators. And generic code now trying to say, is this thing allocator aware? I'll go through the user's allocator trying to say, does this type support my allocator? Great, now I have to sniff out, is the allocator passing as the last argument, or as the first with this different convention, or is the constructor not there, so I have to go back to being allocator unaware? So the syntax associated with this, it's much more expert friendly than we would like it to be. It's much fussier than we would like it to be. So, copy construction is another one of those cases where intuition and experience lead in different directions. It's intuitive that if I'm copying an object and I've not told you which constructor to use, well, there's a perfectly good one in the thing I'm copying from. Where else am I going to find one? I would expect to just copy the constructor. That's the default behavior of allocator traits. If you're in a scoped allocator model, though, a copy where you haven't told it which allocator to use, because this could be happily propagating out into the broader world in a different context, should always follow the rule of, if I've not been told the allocator, use the default allocator. And that's what the select allocator and copy construction is all about. And that's why we have the notion of a default allocator in the PMR model, because if we're not going to pull it from the object we're copying, we have to reach somewhere, so we have this global notion of the default allocator. Now, CP17, we said, nails down the notion of copyalism, so that even though we now fixed our copy constructor to correctly switch to the default to try to avoid leaking the allocator out from the example we showed earlier, you have to now somehow find a way to force that temporary, because now it's at least guaranteed the whole thing, compiler warnings for this kind of idiom, especially when dealing with PMR allocators, a very specific case that can be detected, might start showing up. But yes, this is probably the biggest risk we have with the current PMR model. So, what am I proposing to reduce the friction? I've got my ideal world model. I want to remove all that code and spam from the allocator interface and from using allocators. If I'm in my ideal world, I will have to add nothing to my type that uses allocator aware stuff, and it will itself just implicitly be allocator aware. So the less syntax I have to use to make my type allocator aware and work with it, the better. Simple data structure uses the same allocator throughout. So we're baking in the scoped allocator model because that's how we can safely write code in the same way that just, the objects that use the allocator or the scope below the allocator. And again, I get the benefit of the scoped allocator model for the compact, the local memory allocation. Model becomes, if a type manages dynamic memory, we want it to always support an allocator. So if I'm going to be able to, I'm going to have to do dynamic memory allocation management in my type, I want to make sure that it always uses this allocation system. So the easier we can make that, the better. Allocator aware types will instantly be known to the system. So I can query, is this type allocator aware? And I will have a consistent interface to say, which allocator are you using for a variety of reasons. So we would know that a type is explicitly allocator aware if it says so. We're going to have to find a way to mark the class and say, for this type, compiler generate all implicit stuff. I'm telling you this type is allocator aware. And the notion of simplifying the law at large, a type will be implicitly allocator aware if it derives from an allocator aware class, or it has data members that are allocator aware. It's that a virtual function makes your type polymorphic. We're going to be viable if our data members are allocator aware. You also become allocator aware and opt into all this new behavior, whatever this new behavior I'm about to talk is. So why do we want to be implicit from members? That's a really novel change in the language. Couldn't we just make allocator aware classes derived from a base class that has the right behavior? A more traditional virtual functions inheritance kind of scheme. Well, if we went this way, things become complicated very quickly. Generic code is going to want to have conditional bases to say, is the thing I'm working from allocator aware? I don't want that funky base class, but if I am allocator aware, I now need to derive from that base class. And I don't want people getting into that kind of metaprogramming. But the more important is, Arrays, aggregates, my original sources of friction, they can't work without the implicit behavior, because I can't make them arrays or aggregates. Aggregates can't again derive from types of view tables. I'm getting myself confused now. I think aggregates don't derive from empty types, so without view tables. Certainly native arrays, or in a lot of the other cases where restricted bindings and so forth, will have problems with the requiring a specific base class. And again, it's forcing this extra vtable pointer in all cases. So again, that big padding of the data structure we're talking about. And it's too much syntax for that common essential use case. But my key issues are, A, we're trying to remove friction. We want to remove the syntax. But key is we need to support the whole system, which is arrays, aggregates, lambdas, all these other things that we can't get to in the system today. We want these to just be implicitly grandfathered in if the members, the elements, say we're allocator aware, you need to be allocator aware as well. So properties of an allocator aware type. An allocator aware type will, oddly enough, use its applied allocator to acquire all the memory it is going to need for persistent dynamic storage. There's going to be a consistent customizable API to say which allocator you're using. I'm going to propose essentially that we're going to have like an allocator of function, that, say a hidden friend that can just say, what's the allocator of this type? And with a scoped allocator model, not propagating nailed down, building that into this language facility that we will propose, that the allocator will not change during its lifetime. Why do I need to have this allocator of method to query what the allocator is? Well, some operations, like if I'm going to move, I can move efficiently if the allocators are the same, otherwise I have to end up doing some kind of crazy copy thing. If I want to swap, if the allocators aren't the same, I can't just do the simple efficient thing. I might have functions therefore that have a precondition that the allocators are the same. How do I know that I'm satisfying that precondition if I can't query the allocator or dispatch them go up and then do something different? If I'm trying to build an object before inserting it into the container or into its storage, I'm going to want to build an object using the correct allocator so they can easily move into that storage once I've finished building it. So I need to, at that point, construct it and say, what's the allocator of the object that I'm building it into, so I can build it with the right allocator. Say swap, we have the precondition, which is what we have in C++11 containers, that the allocators are the same. The alternative behavior would be to say, okay, I will make 2 different copies using the appropriate allocators, and I can then just do simple swaps there, so that I can go with a wide rather than a narrow contract, but then swapping is no longer guaranteed, constant time to keep on throwing. So there's 2 different options there, but either way, I need to know what the allocator is. So that's why we want to have a consistent method to query the allocators. How are we going to simplify construction? The key issue here is we have this span of all these extra overloads where we've got the allocators that do take to allocate to the allocators that don't. We don't want to be adding all the allocator overloads and multiplying out the large number of constructors, which means we want to provide the allocator with a method other than as a constructor argument. So this is the key change that we're proposing, or the most visible change we're proposing, is that we're going to add a using clause after a variable declaration, or potentially in a couple of other places, that allows us to specify this is the allocator, or you can see what I say essentially, this is the memory resource, all the way down to the PMR memory resources that I want you to use when I'm building this object. And that will hopefully greatly simplify and pull out a lot of the friction on how you actually write an allocator aware class. So how does that work in an example? Here I'm building a class object. It's a simple object. It has a name as a PMR string because it's wanting to be allocator aware in C++20. I have to, of course, have my allocator type here, and I'm using polynomial allocator. Most of my constructors I've now And to keep life simple, I'm providing a default argument for the allocator, although the move constructor has to be special and split into two, because the move constructor is the one special case I forgot to speak about earlier, where it doesn't work correctly unless I do allow the allocator to propagate on a move constructor. Because if a move constructor did the standard thing of switching back to the default allocator, it's never going to support a move unless I always manually supply the extra allocator. And that's inimical to what move constructors are intended to achieve. So the move constructor is the one special case where we expect that by default, you will just allow the allocator to propagate, and then you can move all your bases and members along with that just as efficiently, and then we'll have all the appropriate properties of doing the efficient move of not throwing and so forth. But then we have to provide an overload of this is how the move constructor works if I'm trying to move with a different allocator. That is something that might be called through trying to then place from an object with one allocator into a vector with a different allocator. It's going to end up calling this constructor. So how does this start simplifying? You've got some of the hints on the screen with the different font colors as we move into my suggested new world. And first thing first, I'm going to have standard PMR2 string. We're not using a PMR string, we're into our wonderful new world, whatever we've chosen to store that. And in this example, I'm putting it into namespace PMR2. We no longer need the type def of my allocator type. And I can generally default all my constructors. Because I'm going with a default constructor where I no longer need to provide the allocator, I can just construct the element in place, and it now no longer needs to be explicit. So because there's no sudden implicit constructor from constructing an object accidentally from converting from an allocator. So that's a nice simplification to begin with. And we can go further, because with this new model, it's the constructor that's going to supply the allocator with this implicit using chained all the way down. So I can safely use the, what's it called, default member initializer to provide the default value up there, and literally default all my arguments. And this is now, again, just going to work nicely. So this is your basic rule of 6 notion. Can actually simplify all the way down to rule of 0. So, okay, it's an artificial example, but the notion of the allocator syntax that was in our way is, I've just now got this one type, PMR2 string, that happens to be allocator aware, means the object is allocator aware, and all those constructors that we have would just now do the right thing. So this is my ideal vision realized. And a simple example, PMR multiple resource, again, not providing any arguments, but yeah, I'm using, as you can see, a regular PMR resource. We don't need to reinvent all the resources that we've already built for C 17 and beyond. So how does this work? Well, again, we're going to stack the allocator pointer away at construction, which is hidden much like the V table, so you don't get to see and interact with this data member directly. But as we go through the construction of all the hierarchy of the bases and members, again, it's implicitly supplied in just the same way through the basic, the member initializer list of the constructors, and for the members that aren't there that get their implicit construction, they get their implicit construction with the allocator. We're going to want a customization API though to give more precise control of this allocator if needed, because you've got issues like standard optional. When it's empty, still needs to know about the allocator. Whereas in the case where it's actually got an object held, we can compress out the space for that allocator by saying, well, when I query the allocator, this is the implicit case, I can optimize out paying storage for that extra redundant copy of the allocator. I can just retrieve it from the base or member that made me allocator aware. And because of the constraint that the whole object class graph has to use the same allocator, it's guaranteed to be the right one. I can pick any of the bases or members. It doesn't matter which one I pick. They will all have the correct results by querying what their allocator is. And that might end up changing all the way down a little bit in theory, but it helps me compress out that little bit of extra storage. So we've gone to the data structures, the ones all the way at the end. They do need to have their own redundant copy. But it allows us to eliminate a bunch of redundant pointers throughout the larger system. So in most cases, allocator awareness will be implicit. This is how we reduce a lot of the friction. We don't expect to have to use this markup, but I've not yet demonstrated to say this class is allocator aware. And that clearly, by its nature, requires a new language feature to support this implicit behavior. We played around with it. In principle, I could have a PMR2 allocator that is my allocator aware type, and now, my standard container is allocator aware for free. And with a bit of clever finagling over the syntax, you could potentially port this into the existing standard library. I'm not clear that that works as seamlessly and doesn't end up with more gotchas than we expect. So I've got it in big flashing orange saying we could do this. I'm not sure the experiment goes quite as well as we might like. So we have the principle I'm calling allocator injection now, which says when at the point I construct an object, that's the time to inject the allocator into the initialization to say whatever initializers are and this. That's part that needs a language extension, such as the using support. New operator is another place that will obviously need something like this. You could imagine something like new paren, like placement, new with allocator, but perhaps the generalization of the syntax works better again at the other end, just with using after the element that I'm constructing. So a couple of ideas how that might work. It means that if you've got an allocator aware type, every single constructor other than the move constructor has an implicit extra argument for that allocator. That's how we get away with having the optional allocator or not. If you don't supply it, it gets populated with a default system resource, a memory resource, or if you do supply a using, that's consistently used for everything. But there's always an allocator therefore being supplied. It's just no longer syntax that the user has to write and be aware of, and that greatly simplifies and removes friction from the system. And again, I say the allocator will have to propagate that all the way down through the rest of the system when it's constructing its bases of members. Early experience with this actually dates back to last year when I gave this talk to CppCon in September. Sean Baxter is a great chap. He's actually written his own C++20 compiler using the LLVM as its backend. Took about the last 3-4 years. And because he's written this with a view to maintainability, it's all been produced by one man. He's got the whole system running. It turns out it's a very neat system for rapid prototyping of new language features and language evolution. I mean, ultimately, he's got his own language or extended C++ called Circle, which gets much more deeply into reflection and some such things. But given he'd got this tool set working around, he thought, okay, I can do that. And about a week later, he implemented the basic using syntax and told us about it. Well, wow, that's interesting. And turned out what he had, his system just built off. If you've got the using the appropriate type, you have to say my type is support with using allocator, and you do a using after, it will look and say, do those things hook up? Great, I can drop that allocator in, and it just works for all possible allocators in the standard library. It wasn't specific to PMR. This was kind of cool. Compiler template argument deduction just fell out for free. And the idea that this could be used to support things beyond PMR blew our mind. It opened up our ports to maybe this can become an even more general facility. And yeah, it's great, the grammar works, we're not bumping into other things. So the grammar space does seem to be available to us. It does work well. And it can work relatively well, even with a language you have to do without doing all the extra work that I want to do to smooth it out all the way through the rest of the system. So this is an example that Sean threw up for us. You see here, we're using the PMR in this case, just again the regular standard line PMR list. construct a list, and he's got his logging allocator that then writes away and logs that he's done those allocations. He's doing the thing he's expecting. And even in the cases embracing this with an auto, it's constructed as temporary and deducing the type and so forth. Again, everything just went through just fine. So the system has had its little quick shakedown, and the idea of the syntax that I'm using seems to be working out. But that's when we start asking all the more complicated questions about how should the facility work in general. And one of the big questions that has been tying us up for a while is the notion of factory functions. These are functions that are going to return a new object by value, something like standard make shared or standard to string. We want to be able to, if we've got a factory function in the allocator aware world, we're going to want to say what allocator the result of that function should use, but we don't get to see the actual code that does that initialization to return that value to us. So what should our ideal syntax be here? Do we want to start passing the allocators as the regular function argument, so all these functions now have to have an additional argument? Or should we somehow find a way to add using support and note that some kinds of functions are special, they're factory functions, so I can add a using argument to those like I could to a constructor? And our notion is, clearly we want to go in the direction of using support. We've got a language facility. It's supposed to be our new common way to provide allocators to things. So that's where we should be looking. And we come up with the notion of should it be explicit, so you can overload with and without allocators, or should it be implicit in some way? And the notion is, if I'm returning by value an allocator aware type, then implicitly I know that my function needs to be allocator aware. I shouldn't need to say anything. It can just immediately, the function knows, yes, this is a factory function, you're returning an allocator aware type. Of course, I support a using, and if you don't give me a using, you get the default allocator. So now we get to the question, how do we actually avoid those, use that allocator within the factory function itself? So I've got a separate question I want to address first, right? The big question that hurts us is, could we find a general pattern for the implicitly generated, when we default, extended move constructor? So we've got the constructor, the move constructor by default just does member-wise move, and the allocators are going to propagate. We know they're all the same, and that's great. And now we've got the move with allocator constructor, move, any value using alloc, and I'm going to do the default implementation. Should it propagate down the, just do, two different styles here. Sorry, I need a glass of water here, I'm drying up. The idiom I was strongly tied to is, it's just like any other constructor. If I'm calling move with allocator, I call move with allocator on all my bases and members. And if that particular base or member doesn't support an allocator, say it's something like standard mutex, it's a move only type, it doesn't support an allocator, I just end up calling the regular move constructor rather than passing the allocator down to it. And this means that if we go back to the original example, I've got a string add a move only value. Therefore, I want to be able to move the string with my allocator. And if the allocator is different, that means I'm going to end up making a copy of the string using the new allocator. But when I call move the value, I want to just plain move it. I can't make a copy. It's not move aware. Option 2, though, says we've got a higher level principle. We're going to test if the allocators are the same on the version I provided the allocator. What do I mean by the same? Given I'm doing a move constructor, well, move constructor, and I'm given an allocator. So the allocator I'm given, I compare that to the thing I'm moving from. And if those allocators are the same, I can just allocate directly to the regular move constructor because the allocators are the same. That will do the right thing. But if they're different, well, I'm effectively making something like a copy. And in that case, the extended copy constructor for whatever it is that I'm dealing with, the constructor with allocator, has had to deal with any object invariance that object might have had to preserve through copying. And that's probably the better choice to delegate to. If they're having to do something copy-like, I don't just try to recreate all that again. I'll just delegate back to the regular copy with allocator constructor. And if that's not available, then effectively my implicit form will be all form deleted or maybe just not exist. I would have the ability somehow to provide the custom log in the case where I did have the string and the mutex, and I wanted to explicitly support that. I could write that code, but in the generic default case, the default idiom would be, no, I will just do this test and delegate to either the regular move or the regular copy with allocator. So we've got these two choices. Is it better to always delegate all the options down, or better to delegate to do one or two more well-defined specific behaviors? And Josh, who's answering the Q&A here, he came out with, he was strongly in favor of option 2, I was strongly in favor of option 1, and I'm a bit hard-headed at times. It took him months to persuade me, but ultimately we came down that there's only more syntax in this extra case, but option 2 is the right answer, because you get, when you look at an example like this. So structure highlight, I've got one of my new allocator aware vectors, and I've got a pointer to one of those elements in the vector. That's my invariant. The invariant is D under focus has to point to an element that's in that vector. So I can delete the copy constructor because by default that's not going to do the right thing. I could also do an implement to say, okay, I know that I was do a search on that vector, say yes, I'm looking at index. Now the point I was looking at was the index position 3. After I do the copy, I will just repoint to whatever's at index position 3, assuming uniqueness of members in the vector. But either way, I'm going to delete it, or I'm going to have to write some code to re-establish that invariant. A copy constructor that defaults is not going to do the right thing. The move constructor, on the other hand, does the right thing. It moves the contents of the vector, it copies across the pointer. I say it does the right thing. As I'm saying this, I've just realized I've now broken the invariant of the thing I've moved from. So that is again, For the example I've written, I would actually have to write the move constructor to make sure I zeroed out again the D under focus. So it's what I get for spotting bugs as I'm going along. In the principle that everything I was encapsulated has already done the right thing, though, this would just default correctly. So option 2 becomes the safe, despite the bug I just called out, version that I'm not going to have in the thing I've moved into a violated invariant if I ever just do the move or the copy correctly. Because I will have written the move and copy here correctly in the first place. If I did the move with allocator property, I would end up violating that invariant. So walk through a bit more detail in the example. So here's what the copy constructor looks like. I just do the obvious initialize the members and then hook up the appropriate property store to preserve it onto the new side. When I come to the move constructor, in theory, in principle, I'm going to default it. Highlighting why that might not be a great idea I thought it was. Does the right thing for the copy, not for the, on the other side, but not for the move. But then I'm going to have this other magical overload that says, I want to delegate to either the move or the copy constructor. But the problem is I can't do a ternary operator to delegate to a different constructor in C++ 2020. But what I can do is I can delegate down to a separate factory function in this case that returns a highlight by value. And all it does is it says if the allocators are the same, using this allocator of query function that I said we would be adding, I can either create a new object by the move constructor or create a new object by the copy constructor. And that then, having done that will return an R value, which means when I delegate that in the call delegating constructor, it always delegates to the move constructor from the temporary that I've just created, that was then created using the correct allocator. Because the move constructor does the right thing to return other without specifying the allocator, because it's a factory function, it picks up the allocator that was supplied at the outset. I might be missing a using. I don't have these on the copy on move. But the principle is that's how you might write something like this in C++20. And this would be the implicit rules for then the extended move constructor in C++ future. And you say, I've got my funky little symbol saying, I need to put something there if we want to have the ability to overload for users to provide their own non-implicit extended move constructors. But that was a syntax corner we've not investigated to duplicate. So where do we go from here? This is a bunch of ideas of what we're talking about, and we want to be able to move this forward towards something that can be a tested proposal where we've implemented and tested and run with a variety of these features to know that what we're proposing to WG21 will do the right thing. So we don't have the complete vision yet, but we do have a good solid framework to build out from. So we're going to try now build or specify a basic feature set and see if we can team up again with Sean Baxter and get an implementation that we can actually write some code against and see how well this works, and then figure out where we generalize for the next steps to have something that is an appropriate thing to bring to WG21. So our basic feature set is we're going to have to pass allocators to factory functions and initialization with the using argument. There's going to be a special allocator type that imbues allocator awareness upon a class. And at this early stage, to avoid getting into the rules about how do we specify what an explicit markup to make a class allocator aware, we're going to build this around to just be a fundamental type that has this property. This is something that we'll be looking to extending and making more user specifiable in the future, especially if we want to support this notion of the scope model for things other than allocators, or for allocators that are not built around the PMR model that they're going to be building around. So there might want to be some more user customization there, but to get the initial proof of concept, we're going to say, we'll just have a fundamental type that says, I am allocator aware, and I'm basically holding a reference or a pointer to a PMR memory resource. So that's what that fundamental type holds. All constructors are then, of any allocator aware type, are then implicitly allocator aware to support its extra using, other than the move constructor, this head splits into two. There'll be an implicitly generated allocator of hidden friend function that will query, as I say, all the way down the flash graph to find the leaf node that says, yes, I've got that. I'm the one that's got the allocator, and this is the PMR memory resource I'm holding. And we'll have the notion of implicit factory functions on it. We're not looking into providing extensibility of factory functions where you might want to provide your own overload means to say, even though nothing in my interface says an allocator aware, I still want you to be able to inject an allocator into me because I've got certain uses for it. So implicit factory functions, they will support the return type. When the return type is allocator aware, the factory function is allocator aware. But that still means, how do you get the allocator into the return value? And we're simply going to say, well, when you're in a factory function, when you construct the object that will become the return value, it will implicitly supply the allocator. And if that's one way you get to then, you just do a return expression. Okay, we'll create a temporary there and push the allocator in. But if we're in a case where the RVO return value optimization applies, we can see early where that is going to be applied and just jump it in there, and we don't need to create that extra temporary. And if we look at features being proposed for C++23, we've got the guaranteed copying proposal, P2025, that again says that there's a different range of places where we can now deduce that even for different, if the return path for the return object is always distinct. So I've been having a multiple if, else, if, else, if, else, and each one has their own return. If I can see that each return chain is distinct, I can still apply the copy of it in the name return value optimization. If I can guarantee that in the language, that again becomes something we can hook onto for saying in that factory function, when I see that the guaranteed copulation kicks in, that's again a place to say when I construct that object, I will implicitly supply the correct allocator there. And my notion for validating this is that a bunch of things that I think will run through this set of types you see on the screen will have a fair idea as to whether or not the code's working as well as you think. That means I'm not going to implement these as alias templates onto the standard library. We'll do distinct implementations of string, vector, and then test it to the vector of strings. And does that code actually look simpler? Does it perform the way we expected? Does it introduce unexpected costs? Are there any extra benefits we weren't anticipating? And that provides a general notion of, can we implement, do the continuous cleanup when we implement that way? Are aggregate classes just supported out the box? Do local arrays just work? In principle, because of you gain the property from your bases and members, standard array, standard tuple, standard pair, these should just work without us having to write new versions of this code. And again, man's expressions. So that's my feature set that I plan to test to gain some confidence that we're on the right direction, and then we can come back and start exactly how do we start formalizing this? How do we start to into something that could then look like a standard proposal? Open questions, argument passing in factory functions. How do we pass the allocator if for functions that are not implicitly allocator aware? And how do you get the allocator that's been passed to your factory function if you want to use it internally and you don't know which of your you've got to have to query somehow the allocator that's passed into you so you can construct the appropriate temporary that then might move into one of the other objects. How am I doing on time? I'm probably down to last couple of minutes. All the constructors on whether or not they're allocator aware. How to utilize the customization points, so I might be able to implement something like standard optional to compress away the storage of an extra allocator if I can either store it when I'm empty or retrieve it from my held object. So you might want to cut how we can customize allocator of. Using in more context, so at the moment I'm just using it for initializing variable expressions, but how about for function arguments and so forth? Using them, I'm running out of time, so I think I'll just pull it there. Do I have any outstanding questions? Okay. Leaf nodes always needing a memory resource pointer sounds like a downgrade. Why do I choose this approach? Well, this is the approach that you get from PMR Allocator. The leafmost node has nowhere else to defer to. If instead of having a pointer to the allocator, where else do I look? I need to be pointing somewhere into the object graph. So I store back a pointer to something else in the object graph that has the allocator. There's no way I can squeeze this redundancy out. So ultimately, we end up with this extra stored allocator in each of the leaf nodes of the whole base class and direct allocation in the graph. I couldn't find a way to eliminate that all the way and usefully slim it down to a single pointer for the whole data structure. If you have ideas, I would love to hear about them. Changing default allocator for a block. Mark, I don't know what you mean by a block, but the notion of the default allocator is, I could probably have spoken a bit more to this. Ideally, we would like the default allocator to be something like a replaceable function. So it's something you can set for the system when you build the program. And if you want to be able to switch around and change it, you just install a default allocator function that has some internal state that says I can switch it around or customize it. The one we have with PMR allocators, you can install whatever allocator you like as a set default allocator, just like you can set a terminate handler at runtime. But there's constraints that generally you don't want to do that after the after maintenance started running, because you don't want multiple different threads playing around with the changing the default allocator. But and that's why again we'd rather have it as a replaceable function. But I know Microsoft always have concerns with the notion of replaceable functions, so whether we can go that route is again something that's still in our investigation line. Should you tell me what you mean by a block?
I think he's asking about using a different allocator for anything that doesn't specify an allocator within a particular scope. So we've talked about doing this.
Okay, changing the default allocator within a small region. Okay,
so we've talked about doing this. I think that we were trying to come up with the right litmus test for how to identify objects that won't escape the block silently and outlive that allocator, causing harm.
Yeah, sorry, I misread. I need to change my question. I read for as with, so my bad.
Yeah, that was basically my question.
But again, we're also trying to contain the initial feature set with the minimal we need to usefully demonstrate what we're trying to do. So can we get the whole set of the basic cases I highlighted in the previous slide? And best then we want to look into a variety of extensions. One of the other things is trying to have this use in syntax for things other than allocators. And we had a great brainstorming of lots of ideas of where this might work. And then we realized we weren't the experts on any of those domains. So trying to prematurely generalize the feature for other people might find this useful. We want the people who will find this useful to come to us, and then we can adapt and clean up. The basic using idea seems right, but when you start using potentially multiple things, how do we extend that? How do we signify something that interoperates with the using system? That's why for the proof of concept, it is going to drop down to it will be a specific fundamental type, and that will definitely not be the final proposal. I don't have any other outstanding questions. So with that, thank you.